Okay, so let me start. So today is my final lecture. And so just to remind you guys what we did last time. So last time we started talking about relics, leftover particles and fluctuations from inflation. And in particular, introduced the standard calculation for computing the effect of quantum fluctuations during inflation. And we were doing this for massless fields. And I told you that there are two massless fields that are guaranteed to exist in all inflationary models, namely the curvature perturbation and the graviton. And so we computed the spectra, the 2-point functions, for both of those massless fields. But ultimately, of course, our goal somehow in the next, and with future experiments and theoretical developments, is to learn more about the physics underlying the inflationary expansion. And it's hard with just free fields to kind of uncover that physics. In particular, what we have measured, arguably, is the 2-point function of scalar fluctuations. That 2-point function is nearly scale invariant, so it is parameterized by just two numbers, an amplitude of scalar fluctuations, the famous 10 to the minus 10, and also a deviation from scale invariance, the parameter ns. And so it's hard to reconstruct what exactly happened at the microscopic level from these two numbers. Okay? If you're very lucky, we might get a third number, which is the tensor to scalar ratio. But it's still hard to uncover exactly what happened. That number would be incredible, of course, and it would tell us the energy scale at which inflation was operating, so it's a very good hint, of course, for learning more. But it would be nice to have more than just these handful of numbers available. And so that brings us to discussing if there could be possible imprints of interactions during inflation. So rather than just studying the free field limit, it's like in particle physics if you were to just know what propagate is. Okay? So then you would know how particles go from here to there, but you don't know how they interact. Okay? And so, of course, that's very limited information. And so today we want to discuss the possible influence of interactions. And we will see that will give us information that's encoded not just in numbers, but momentum-dependent endpoint functions. Okay? And so in principle, that contains a lot more information than the power spectrum. Okay, so with that motivation, let's start talking about... Yeah, oh yeah.
If I would reinstate H bar in the calculations previous lecture,
yes.
Would it roll or would it cancel out?
No, it will be there. These are H bar finite H bar effects, and so if you put H bar to 0, things go away. These are genuine quantum fluctuations. So yeah, if you were to reinsert it, actually would be a good exercise. We never do this, because it would be nice to just check that things work out dimensionally correct if you do that. And then the power spectrum should have a H bar in it. And it comes from the commutators. The commutators have an I H bar there. If you trace this through the calculation, the end result should be proportional to H bar. Yeah. Any other questions about last time? No? Okay, so then let's move on. And so I want to discuss primordial interactions. So let me just repeat that so far what we have studied were free fields. We just looked at quadratic actions, and from those quadratic actions, we computed two-point correlation functions. For example, this one. Which in Fourier space becomes the power spectrum. And in fact, one remarkable feature of inflation, or what we already know, is that those two-point functions carry kind of the dominant effect of the statistics of the fluctuations. Yeah? Any type of deviation from this Gaussian behavior, any higher point functions are kind of small deviations around some predominantly Gaussian distribution functions. Okay? That didn't have to be that way, but it happens to be the case, and so that's something we're going to be exploiting, because then we'll be able to describe interactions perturbatively and look at higher point functions as perturbative corrections to these Gaussian statistics. So that's what we want to do next. We want to look at interactions. And so, yeah, as long as these interactions are perturbative, we can start with the lowest order higher point function that's beyond this Gaussian limits, which is the three-point correlation function. So instead of 2 insertions of zeta, we're going to have 3. In Fourier space, this is called the bispectrum. Notice that the power spectrum, this two-point correlation function, had a momentum-conserving delta function. The bispectrum also has to have a momentum-conserving delta function. Now the sum of all 3 momenta has to vanish. Okay? And so this just follows from the fact that the universe is homogeneous. It doesn't depend on location statistically. And so you have momentum conservation for each of these waves. And the same happens at the higher point level. So that means that these momentum configurations that you can have are not arbitrary. They always have to form closed triangles. Okay, so this shape of the bispectrum is going to be characterized by different triangle configurations, and there's always this closure condition for the momenta. Then there's a momentum-dependent function which plays the role of the power spectrum P here. This is the bispectrum B. This function is now a function of the absolute values of the wave numbers. At this level here, this was just a consequence of the universe being isotropic, so it has to be invariant on the spatial rotations, and the same applies to at higher point level. And then I'm going to be using the convention that I'm also going to be factoring out some overall momentum factors that make this bispectrum dimensionless. And in this case, this will be 2 pi squared all squared, k1, k2, k3 squared. Okay, the bispectrum has dimensions 1 over momentum to the 6th. Okay, and so I've factored out a symmetric combination of these 3 momenta that carries exactly the same, the right dimensions, so that this function here is dimensionless. Okay. Now, if the fluctuations are scale invariant, we can write the following ansatz for this function b of zeta. So we then write this function here in the following form. There's an 18 over 5, which is a historical accident. Then there's an amplitude called FNL, which determines the size of this bispectrum. There's then a shape function, which I'm going to call S, which depends on 2 variables, x2 and x3. And x2 and x3 are defined as the following momentum ratio. It's the ratio of k2 over k3 divided by k1. Okay? So because of scale invariance, this a priori arbitrary function of k1, k2, and k3 only depends on these two momentum ratios. Okay? So in terms of this picture of triangles, it only depends on the shape of the triangle and not on the absolute size. Okay? So as I'm rescaling a given triangle to make all sides bigger, the signal doesn't change. Okay? That's a signature of scale invariant fluctuations. If that wasn't the case, then you could still write it this way, but then this FNL parameter would be dependent on the overall size of the triangle, some measure of the overall size of the triangle. Say the sum of all three would then appear in the definition of this FNL. Okay? But we're always going to be looking at scale invariant fluctuations, so some ansatz like this applies. And then it's also proportional to 2 powers of the power spectrum evaluated at some fiducial scale k star. Okay? So as I said, this parameter here is the amplitude, and this is the shape. And I should say, in order to make this split into amplitude and shape unique, I'm going to be normalizing the shape function such that in the equilateral configuration, this function is 1. Okay? So if I'm choosing these two momentum ratios to be equal to 1, equal to each other, and equal to 1, then the shape function is normalized to be 1. And that uniquely specified what I mean by the overall amplitude of this bispectrum. Okay? Let me continue here. So this will be a function of triangle shapes, but there are 3 triangle shapes roughly that kind of carry distinctive information. So let me point them out. So if I have very squeezed triangles, so for example, if I take this ratio x3 and let it go to 0, this means that the momentum 3 is much smaller than the momentum k1. So one of the wavelengths is very long relative to the other two. That corresponds to very squeezed triangles. And as we will see later, in fact, this limit is going to be very crucial. This limit is what's going to carry information about extra degrees of freedom. Okay? There's going to be a very powerful theorem that was first introduced by Juan, in fact, and then generalized by Criminelli and Saldarriaga, that proves that in any scenario where you have a single degree of freedom during inflation, this limit vanishes in a very specific way. So this soft limit here has a specific vanishing behavior in this case. So any deviation from this vanishing is a signature of extra degrees of freedom. So that's in fact going to be our particle detector. Okay? Seeing a deviation from this single field theorem will allow us to identify new degrees of freedom. Another important limit is taking the limit of an equilateral triangle. So in my parameterization, this means I'm choosing x2 to be equal to x3 and equal to 1/2. Sorry, 1. Okay? It turns out this equilateral configuration arises from higher derivative interactions, for example. Okay? And so we will see an example of this appearing later. And then finally, also, you could have a folded triangle. x2 equals x3 equals to 1/2. And such a folded the signal peaks in such a folded configuration, for example, if your inflation starts with some excited state and not with the Bunch-Davies vacuum. Okay? So these different momentum configurations carry different amounts of physical information. Well, if I fold the triangle in this particular way, then one length is twice the other two. And let's say I'm picking this length to be the length associated with K1. Then this is K2 and K3. So these ratios work out to be 1/2. No? If I choose this to be K1, this K2, and this K3, I'm going to collapse it in a symmetrical way. And then these become equal, and exactly 1/2 the size of the one that I'm normalizing it by. Well, it's a limit, of course. Yeah, it becomes, yeah, just like this squeezed limit here. This one I'm approaching, yeah, and I'm particularly interested in the momentum dependence as of course, the limit of this going to 0 corresponds to infinite wavelength. That's not really what I mean. Yeah, I just mean that it's much bigger than the other two. And here it's the same. I just mean that this angle here approaches. Yeah. Okay, and then just let me give you an impression for what we know at this time about this amplitude. Yeah, sorry. Yeah, so it corresponds to the correlation between one very long wavelength fluctuation and two short wavelength fluctuations. So it describes, in fact, the variation of the power spectrum as a function of position. Yeah, as I go from one place in the so one way of measuring this limit would be to make power spectrum measurements at different patches in the universe, go from one patch to the next, and if you find some long wavelength correlation between the measurements of these power spectra, that's what this limit is. Yeah? So making one momentum mode very small means you have one very long wavelength, and it acts like a background that modulates the short wavelength power spectra. Okay, so let me give you a sketch of kind of observational constraints on this amplitude FNL. These constraints are dependent on the shape, but I just want to give you a rough impression of kind of what's constrained at this moment. So let's start by FNL of 10 to the 5. FNL values of bigger than 10 to the 5 in some vague sense are meaningless, okay? Because that's the regime where this entire perturbative expansion, like this expansion into a 2-point function, 3-point function, and so on, breaks down. Yeah. So we already know that the universe is to a leading approximation Gaussian. So we don't think we're living in a regime where that's the relevant regime to be talking about. But strictly speaking, it's not computable. So maybe magic can happen. Okay. But I'm not going to be relying on this magic. So we're not going to be looking at these kind of. One should then be looking at different statistics. It's not a meaningful statistics to just look at the 3-point function and ignoring higher point functions in this regime. Okay. So this is non-perturbative. Then there's another interesting lower limit, which is 10 to the minus 2. And that I like to call the gravitational floor. Okay. And so just simply by gravitational nonlinearities in the Einstein equations, you will generate, even in slow roll inflation without additional degrees of freedom, you will generate this amount of FNL. Okay. So this is somehow the minimum that you will get just by the fact that gravity is a nonlinear theory. Okay. And we're going to be looking for additional nonlinearities on top of this, things that have to exist by the fact that, gravity exists. Okay. So that's the gravitational floor. So in principle, we have 7 orders of magnitude that are of interest to us, where we could search for new physics in those 7 orders of magnitude. So current observations are constraining 3 orders of magnitude, roughly. So the upper limits on FNL are between 100 and 10, depending on shape. Squeezed limits, things that peak in the squeezed limit are more constrained than things that peak in the equilateral limit. And that's just because the FNL is actually normalized in the equilateral limit. So if something peaks away from the equilateral limit, the normalization amplitude will be constrained to be smaller because you have more signal away from where you actually normalize the amplitude. Okay, but that's really just actually an artifact of the way this number here is defined. Okay, it's not really the case that it's more or less Gaussian in that limit. Okay, so there's an order of between 10 and 100, I would say, is the upper limit for all shapes that are scale invariant. And so this regime here is ruled out. Mostly by CMB data from the Planck satellite. Okay, and so we are left with these 4 orders of magnitude, which, for the purpose of this discussion here, I'm going to be calling our window of opportunity. Okay, and so I think this picture here should make it clear that it's not correct when people say, Planck has ruled out non-Gaussianity as a possibility. There are 7 orders of magnitude a priori that would have been of interest. 3 orders of magnitude have been ruled out. 4 orders of magnitude are still left. Okay, it's true that these 4 orders of magnitude are very hard to further constraint, and we're going to discuss this maybe towards the end. But that's just an artifact of human detector sensitivity or things like that. It's not necessarily a feature of nature. Okay, so there are 4 orders of magnitude that, in principle, still could be having signals hidden in them. Okay, any questions about this intro? So far, this was mostly bookkeeping. I just introduced the basic statistics that we want to look at. And now we want to discuss a little bit what physical mechanisms can create signals in that statistics. All right. Okay, so let me first give a brief discussion of how we compute these non-Gaussianities in inflation. And so the main formalism for doing this is what Hong Lui already introduced, which is Stringer-Keldysh, or in formalism. So he already explained that in particle physics we usually care about in-out amplitudes. I learned from Juan in his lectures, of course. Yeah. So the in-out amplitudes, like scattering matrices, that we usually compute in particle physics. While in cosmology we're interested typically in in correlation functions, and we have to think carefully about how we evolve the in-state under the influence of interactions. Okay? So I don't want to go through this discussion. You can see some slightly more detailed discussion in my lecture notes. And particularly, you will see a derivation of this master formula that I'm going to be writing down in a moment. So the only thing we will need from that discussion is the following correlation function. So if you want to calculate the expectation value of some operator Q, or a string of this operator here can be a string of operators made out of zeta, for example. So 3 factors of zeta would give us the bispectrum. Evaluated at some late time tau. This can be expressed in terms of the vacuum state of the free theory. Then there's some unitary time evolution operator of this state in the presence of interactions, which takes the following form. It's the interaction Hamiltonian in the interaction picture. This operator Q in the interaction picture. And then it's going to be sandwiched with another vacuum state, and that one has to be evolved along the other branch of this contour. Okay. So the derivation of this formula, you can see, for example, you can see a sketch of that derivation that I tried to squeeze onto 2 pages in my lecture notes, but that's actually not a complete derivation. The complete derivation maybe takes about 10 pages, and it's derived in a paper by Weinberg. And then Maldacena was using this, but not actually deriving it again in his famous paper. Okay. Okay. So these are kind of just time ordering and anti-time ordering operations and so on, as usual. So we're going to be exclusively dealing with things at tree level. So then this expression here can be simplified by expanding out these exponentials at leading order in the interaction Hamiltonian. So one gets an integral from -infinity to tau, d tau prime, the expectation value of the commutator of this operator Q at time tau with the interaction Hamiltonian at time tau prime, sandwiched in between the vacuum states of the free theory, okay, plus higher orders. So this contribution here describes tree-level processes. And then if you want to get more accurate results, you have to go to higher order, and that would be representing loops. Okay? But this is now a well-defined machinery that allows us, if I gave you some higher order Lagrangian, has some cubic interactions in them, I know how to, in the interaction picture, to evaluate the evolution of all the fields. It's just a free field evolution that we had last time. We had the same mode functions we had last time. Those mode functions would have to be substituted into this operator here and this operator here. You would evaluate this commutator by using the commutation relation for the creation and annihilation operators as before. And then you'd have to do one time integral. A time integral can be subtle and so on, but nothing beyond your powers. It's not different from those type of integrals in usual field theory. Okay. So in fact, in the lecture notes, I show you some explicit examples of 3-point functions that are computed for certain interactions that I introduced. Okay. And so I'm not going to do these calculations here. They're a bit involved. But if you really want to learn this stuff, I encourage you to reproduce some of these results and tell me if I get my signs wrong and those kind of things. At the moment, I think all signs are like arbitrary in my notes. And so I've decided there's a 50-50 chance of any signs being either plus or minus because my signature changes and it's a total mess. So, but I didn't have time to change this last week. So once I'm done with this, I will spend a week figuring that out. Okay, but just a warning: when you shouldn't take me at face value for these. And factors of 2 is similar. Okay, so let me just then give you an example for this, which is the gravitational floor. So this is as I said, what I mean by this is the minimal amount of non-Gaussianity that's generated in single field slow roll inflation. So what do I have to do to calculate this? I need to start by expanding the inflationary action to higher order than we did yesterday. So in particular, the action was the following. So Einstein-Hilbert, and then the slow roll part of the action. Okay. So we would like to expand this to 3rd order in fluctuations. And in particular, those will be fluctuations in the inflaton, or we can choose a gauge where there are no fluctuations in inflaton. Then it's fluctuations in the zeta component of the metric. And in addition, we'll have the 2 constrained metric perturbations, and so we will have to solve the constraints. One nice feature of only going to 3rd order is that we only have to solve the constraints to first order. Okay, I leave it to you to think about why that's the case. Okay, it turns out you don't have to expand the constraints to 2nd order because actually the solutions at 2nd order for the constraints will be multiplied by the linear equation of motion and so on. So that all of this is explained in more detail in my notes. Okay. But here I just want to give you the final answer. So when you go through this, you get the following cubic action for zeta. So there's a overall measure factor a squared as before. There's a normalization which is given by epsilon squared. Remember, epsilon is the slow roll parameter that we had last time. And then we will have a certain, a number of cubic interactions in zeta. So for example, there's an interaction that looks like this: zeta times zeta dot squared. And in fact, and then there's a large number of additional interactions, and I don't want to write them out. Okay, you can look at Maldaceno's paper. And in fact, I can't advertise this paper enough. I've done it twice already, 3rd time. If you really care about this stuff, you should read this paper, and then read it again. And then you will see what this action looks like. It's actually quite involved. It has some non-local looking things, because when you plug back the constraints into this, it like kind of looks non-local in zeta and so on. It has things that are proportional to the linearized equation of motion that can be removed by a field redefinition and so on. Juan did this all very elegantly, okay? And so you can look it up there. I just want to give you a flavor for what you would get. And so in order to give you a flavor, I just focus on one specific interaction, which is this one, okay? So what we could do now is we could take this action and we could substitute this into this equation, which I'm going to be calling star. So substituting this into star would give us the bispectrum for single field slow roll inflation. And in fact, so in my notes I do this. I actually calculate this. I slaved away for one day. And so at your benefit, you can go through the steps if you want. Okay. Let me just highlight two important features of the final answer that you get. So without writing out the full momentum dependence of the bispectrum, which we could do, but not worth the effort at this point, I think. So the first thing to note is that the overall amplitude of this bispectrum is small, okay, as I already indicated in this plot over there. And in particular, it scales with this slow roll parameter epsilon and its sister parameter eta, which is related to the time variation of epsilon. And this size, basically, it's easy to see where this comes from. It comes from the fact that the overall normalization of the three-point interaction here scales as epsilon cubed, while the quadratic action scaled as just epsilon. Okay? So just very roughly, if you were to take the ratio of the cubic Lagrangian divided by the quadratic Lagrangian with an extra factor of zeta to make the powers of zeta equal, that ratio evaluated at horizon crossing would become just epsilon, because there's epsilon squared upstairs and then cancelled with an epsilon from downstairs. Okay, and so that explains the small size of this interaction. Okay, and yeah, and the underlying physical reason is that this interaction just comes from the nonlinearities of gravity. Okay, and in the constraint Einstein equations, you will see that these nonlinearities are suppressed by epsilon. And in fact, if you take the limit epsilon goes to 0, you decouple the metric fluctuations. And so that's why you know that the constraint equations have to scale with epsilon. Because in the limit where you make it perfect is that there shouldn't be such a back reaction. And the back reaction is determined by the size of deviation from the zeta space, which is epsilon. Okay? So this is therefore typically of order or smaller than 10 to the minus 2. Okay? So it's 4 orders of magnitude away from what we can observe right now. Okay, then the second thing to point out about this result is if I take the limit of x3 going to 0, so the squeezed limit of the shape function s, what I would find is that this is twice epsilon plus eta times x3 to the minus 1. Okay. Does anybody remember where this combination 2 epsilon plus eta came up before? Have you seen this before? Yeah. So we had this yesterday. So what else was determined by 2 epsilon plus eta? Not R. R was 16 epsilon. NS. Yeah. So this combination, in fact, is exactly 1 minus NS. Which means that this actually vanishes for scale invariant fluctuations. Okay. And in fact, this is not an accident. This is a special case of a more general theorem that's called the single field consistency relation. And in fact, already in Juan's paper, when he discovered that this was proportional to ns minus 1, he made a nice remark that this is more general than for a single field, and has kind of a proof in like 3 lines of Juan. Okay, and then there was a whole paper by Creminelli and Saldiaga that actually spelled out a more detailed proof of this, and I've gave my version of that proof in the notes. Okay, so what you can actually show is, because what this limit, as we said, in real space corresponds to It corresponds to taking a very long wavelength mode and correlating it with two short wavelength modes. Yeah. But if the universe has only a single degree of freedom, then this effect of a long wavelength mode, this is like a classical background. It has already crossed the horizon when the short modes will cross the horizon. So it will act like a classical background as far as the two short modes are concerned. And you can, in fact, incorporate the effect of this long wavelength mode in a coordinate redefinition. Okay? No, remember that zeta, remember how zeta appeared in the metric. It appeared as an overall conformal factor in front of the spatial coordinates. Okay, so it's a local varying coordinate, but when you make the wavelength very long, it's like a constant rescaling of the coordinates. Okay, and so that's the gist of why there shouldn't be any correlation if this thing is scale invariant. Okay, and so this has been formalized, and so the statement is that if I take the limit of one of the momenta to go to 0 of the bispectrum B zeta, I will always get 1 minus ns times the power spectrum of K1 and the power spectrum of K3. Okay? And so this proof is due to Criminelli and Salderegger. It's not a hard thing to prove. Okay. Okay. So this means that in quite generally, as long as I just have a single degree of freedom that generated the zeta fluctuations, so for just purely adiabatic fluctuations, this would vanish if the fluctuations are perfectly scale invariant, and I only get a small deviation that's proportional to the deviation from scale invariant in the general case. And so what this means is that if we ever were to detect a larger deviation in the squeezed limit from this behavior, this would be a diagnostic for extra fields. It's not something I can possibly generate with the inflaton itself. Okay? And so we want to exploit that feature in the following. Any questions about this? Sorry? Imagine I found a signal that has some non-vanishing, bigger than the expected 1 minus ns contribution to the squeezed limit of the bispectrum. And then the very first thing I can conclude from this is there had to be additional fluctuating degrees of freedom during inflation that converted their non-Gaussianity to the observable non-Gaussianity that we see. Okay? It's a very clean test. That's why people are excited about having this theorem. It would immediately allow it to rule out that single field slow roll inflation was kind of the model of the world, because it doesn't allow this type of behavior.
So how will we get extra fields?
We will see. That's what I want to discuss in the rest of this lecture. Exactly, examples of extra fields that fluctuate during inflation that will lead to distinctive behavior in the squeezed limit. The first thing they will do is they will lead to a signal that's bigger than this expectation. Okay, and then and then there will be certain scaling behaviors that will even tell us about the nature of those fields, what type of fields they are, what their masses are, what their spins are, and so on. Yeah, that's what I want to do in the rest.
Sorry, haven't we already measured 1 minus ns?
We have.
So don't we know that this limit isn't 0 anyway?
Well, but it's small. I mean, remember that 1 minus ns is of order percent.
Sure. So you mean?
So that's the 10 to the minus 2 level
okay.
Gravitational floor. So I'm talking about discovering something above the gravitational floor. Okay. One extra thing maybe to say is there's actually some ongoing debate. It's probably settled in the mind of Matthias, but maybe other people are still debating it. That even this 1 minus ns is not observable. This is what he thinks, and I think he's right, okay, is that this 1 minus ns is an artifact of using co-moving coordinates in an unperturbed universe. In a real experiment, however, you're not measuring co-moving coordinates in a homogeneous universe. You're measuring physical coordinates that incorporate zeta fluctuations. And once you go to the physical coordinates that you use in your measurement, this 1 minus ns will actually go away. So that's even a sharper prediction, that you should literally, in the physical coordinates, not the co-moving unperturbed, okay, you should really find 0. The fact that this is 1 minus ns here is really telling us it's exactly 0. There's no correlation when expressed in physical length scales. Okay, so it's actually a stronger statement even than this appears to make it. Okay. Any other questions? So Miranda said she thought she was German for a while, and I'm German, so I'm allowed to use it. Okay, so then let's get to the final part of this course, which is discussing the effects of heavy fields during inflation. And so I want to actually start off by making some general statements about massive fields in de Sitter space. That may be useful for you to know in their own right. So massive fields in de Sitter space. So they can be classified just like in Mink's-Poincare. You can classify representations in terms of mass and spin. So let's start with actually something we have already seen. So if you have a spin s equals 0, so a scalar particle, something we saw last time was that there's a distinctive change in the behavior when the mass crosses a certain threshold, which was given by 3/2 h. Okay. So actually, maybe I should try this a little bit. So for masses greater than 3/2 h, we call that the principal series, and masses less than 3/2 fall into the complementary series. Okay. So one thing we, for example, saw last time is that the power spectrum of fields with masses greater than 3/2 h becomes exponentially suppressed. There's a Boltzmann factor that suppresses the amplitude. And we saw that particles with masses less than 3/2 h are not scale invariant, okay, have a deviation from scale invariant proportional to the mass, and they're actually time dependent at late times. So in particular, this time dependence is going to be interesting to us. So if I were to draw the mode function sigma k of tau as a function of tau, so there's a particular moment in time for given k where the mode crosses the horizon. If the field is massless, then it's frozen after that moment in time. So for m equals 0, we expect the mode function to have constant amplitude outside of the horizon. For m greater than 0 and less than 3/2 h, we expect a monotonic decay of the mode function that depends on the mass of the field. So the heavier the field is, the faster it will decay at late times. And in fact, this decay later will imprint itself into a momentum dependence in the soft limit. Okay, so we can already see this happening here. And then if the mass is greater than 3/2 h, first of all, the amplitude has an overall e to the minus pi m over h. So it will have suppressed amplitude. And then it will decay and, in addition, oscillate. Okay. And in particular, this subhorizon behavior, it goes as tau to the 3/2, the cosine of m over h, the log of k times tau. Okay? So it will experience oscillations outside of the horizon with an oscillation frequency that's set by the mass in Hubble units. Okay? And so later we're going to see that these oscillations will get imprinted in the squeezed limit momentum behavior. So by detecting those oscillations, we will be able to detect the mass of the particle. Okay. There's an overall factor of tau to the 3/2, which is exactly the square root of a to the minus 3. Okay? So when you square this, you get kind of a number density of these particles. So the a to the minus 3 is telling us nothing else that the number density in an expanding universe is decreasing as a to the minus 3. So that's what's indicated by this suppression due to the t to the 3 halves.
Does tau increase to the right?
Huh? Tau is during it, so it increases from minus infinity to 0. So that's why this is a suppression factor, because it will at late times that's the limit of tau going to 0. Yeah. So in fact, this factor is partly what's going to make it hard for us to measure the squeezed limit, because the signal becomes smaller and smaller at late times. And so the correlation between a long and a short mode becomes smaller and smaller because of this dilution effect. Okay. By which?
Yeah. Where is the horizon outside the horizon?
This is inside the horizon. So we're starting from minus infinity and we're going towards 0. Horizon crossing corresponds to minus tau equals to k to the minus 1. So it will be at different times for different k modes. Okay. Okay. Tau is a measure of the horizon, and then in terms of wavelength, you can relate the two like this. Okay. Any other questions?
This mass is smaller than 2h.
Yeah.
Does it go to 0 eventually?
This thing?
Yeah.
Eventually, yes. Yes, exactly. It will go as some power. It goes as some tau to the nu, where the nu is exactly the same nu as we had last time. I think this nu is the square root of 9 over 4 minus m squared over h. Sorry, maybe with a. I think it should have a 3/2 plus or minus nu are the two solutions, which means in the massless limit, okay, there's a mode that's just constant, because in the massless limit this becomes 3/2, and so you have 3/2 minus 3/2 gives me tau to the 0, so that's a constant mode. And then in addition, I have also a decaying mode which goes as tau cubed, even for the massless field. That's just like so we have two solutions. Here for massive field we also have two solutions. And if the mass is small, I could expand this, yeah, and I would get that this would be tau to the plus or minus mass squared over. Well, let me not say commit to this plus or minus sign. But what you would find is that, yeah, it's polynomial in tau. So in the limit tau going to 0, this vanishes at some rate. And the larger the mass is, the faster that vanishing behavior. Any other thing? Okay, so this was for spin 0. Similar things happen for higher spin, although there's just a few subtle differences that are kind of interesting. So let me mention them. So now consider particles with spin greater or equal to 1. And so in the notes I give the most general behavior for arbitrary spin, but let's just focus on an example of, say, spin s equals 3. So again, we can draw distinctive behavior as a function of the mass. And so there, something special happens at a mass of 2 Hubble, a mass of 2.4 Hubble. I think this 2.4 actually stands for square root of 6. And then 2.5 Hubble. Okay. It turns out this 2.5 is the division between the principal series and the complementary series. Okay. With complementary series ranges from 2.4 Hubble to 2.5 Hubble. It's a pretty narrow range for spin 3. So in fact, this bound, this critical value of 2.4, or square root of 6 Hubble, in this case, is a generalization of what's typically called the Higuchi bound. Which in general terms is described as m squared has to be greater or equal to s times s minus 1 times Hubble squared. Okay. So it turns out that masses that violate this Higuchi bound would lead to non-unitary representations in the de Sitter representation theory. Okay. And so these are therefore forbidden. Okay. So this regime here is forbidden. You see that you get no bound for spin 0, and you get no bound for spin 1. So the Higuchi bound starts at spin 2. And in fact, for spin 2 in particular, it's called the Higuchi bound, and for spin higher than 2, it's a generalization. Okay. But there's this minimal mass that you have that you shouldn't be crossing in the Sitter space if you want to have some unitary representations for these particles. There are 3 special cases. So you can, of course, you can have higher spin particles. Well, that's maybe still subject to debate, but it's interesting to consider higher spin particles with mass 0, like they appear in Vasilyev's theory, for example, or this particular case here of twice Hubble. Okay, and so these 3 points here, I'm not sure if to include this or not. You could. There's a bit maybe semantics. These are often also called the discrete series. And particles with those masses are actually sometimes called partially massless particles. Okay? Imagine you start with massive particles that have a certain number of degrees of freedom, in particular for a given spin, they have a certain number of longitudinal components. And then you remove some of the longitudinal components, not all of them. If you remove all of the longitudinal components, you get a massive, massless higher spin particle. If you remove only a partial set of the longitudinal components, you will get partially massless fields. So a partial gauge symmetry enhancement, and they will have finite masses, but very fixed discrete values. You can't scan those masses continuously.
So I'm confused. So 2H is allowed despite the bound?
Yeah. The bound doesn't apply. The bound applies except for these discrete exceptions. Okay? So there's a discrete series of points that is allowed, but everything outside of that is not.
What's the discrete series?
For s equals 2 is actually degenerate. For s equals 2, that is discrete point. In the notes, I give you a general formula actually for these points. These points are given in terms of the mass of the spin, and then another parameter t called the depth, which ranges from 1 to s minus 1, and can take s minus 1 values. And so that's why you get higher. You get more of these points as you go to higher spin. You get 1, 2 until s minus 1. And for s equals 2, you just get 1 point, which is exactly the Higuchi bound.
So is this in a sense because we have to project like the lower rank tensor from the genuine higher? So in some sense, it's not like pure s equals 3, but it's the kind of a residual that has 2 components in it.
I don't think that's it. No, no. So the spin is a genuine spin equals 3 component. It's just that you have removed some of its longitudinal modes, okay, and that creates a partially massless field. It's a hybrid. It's a kind of an in between. It's not a massive gauge field, and it's not a massless. It's in between, because for higher spin you can have several longitudinal components, so you can have can keep some of them and remove and induce partial gauge symmetry by removing some of them. Okay. Okay, but I don't want to get hung up on this. They're not going to play any role in what I'm going to say later. It's just an odd thing that, for example, these things doesn't happen in flat space. Partially massless fields, have no flat space interpretation, and so it's cute. Okay, but and there's certain features of these things we can talk about later. Yeah.
So this is strict de Sitter, right? H is not.
Yes. At the moment, it's strict de Sitter, but this kind of classification, I think, does survive when you go beyond strict de Sitter. Okay.
H is not very good.
Okay, very good. Actually, maybe this is, maybe I shouldn't have been so quick. So in a non-strict de Sitter, actually, it's not entirely clear, this discrete series, for example, how to interpret them. I think, and it's actually something that me and my postdocs have looked at a little bit, whether you can actually define those things as curvature coupling, as some certain, let's talk about it later because it's going to get very detailed. But it's not 100% clear, I would say. So that's a good point. But there's a feeling that this kind of Higuchi bound, if you just have a small deviation from Sitter, the Sitter shouldn't go away completely. That would be pretty radical, but maybe it's not completely proven. Okay. Okay. Any other questions? Okay, so what we'd like to do now is, ask, what would happen if I had those extra massive fields during inflation, and then we will see that the expansion of the space-time can create them. But then because they're massive fields, they will decay back into lighter fluctuations, like the inflaton. And so we would like to look for the signatures of those effects. And in fact, there are two types of signatures which I want to distinguish, and I call them local and non-local. And so let me give an example of a Lagrangian that has the usual slow roll Lagrangian for the inflaton, but then in addition there's an extra scalar sigma with a mass m, and then there's a coupling between sigma and phi, and just for purposes of illustration I'm going to choose this particular dimension 5 operator. So now there are two different regimes. So if the mass of this extra scalar m is much larger than h, then I expect that I should be able to integrate out this field sigma. Okay, and in fact that's true. So in that case we can integrate out the field sigma. And so in particular, at the lowest order, what we're left with after this integration out is an effective Lagrangian for the light inflaton field itself. So that's the original slow roll Lagrangian, but now in addition I get higher order, higher derivative interactions. For example, the leading one would be partial phi to the fourth 8 lambda squared m squared. And there will be higher derivatives that come from expanding out the propagator of this field sigma that would involve boxes over m and so on. So there's an h over m expansion that I'm dropping here. Okay, so that's just a leading term that I would get by combining two of these operators with a sigma as an exchange, and then two kinetic terms combined gives a kinetic squared basically, so partial phi to the fourth. Okay. So this is the leading higher derivative interaction that I would generate from this. So, and in particular, what's important here is that this is local. So I will generate a local interaction. And so a cartoon for this local interaction would be something like this. So it has 4 legs, which are the 4 inflaton fields. This is supposed to represent conformal diagram of space-time, where space runs this way, time runs this way, so tau, and x this way. Okay. So there's a point-like interaction between those four field values. And of course, this locality is not a surprise. This is what we expect of an effective field theory at energy scales lower than the mass of the particle that I've integrated out. Okay, but this interaction is now an interaction for the background inflaton field. What we observe is not the background interactions, but is interactions in the fluctuations. So if I were to evaluate split the field up as last time into a background value and a perturbation var phi, then I can evaluate 3 of the legs in the fluctuations and just 1 of the legs on the background. And this will generate a bispectrum of inflaton interactions. And And it's straightforward to relate that bispectrum to a bispectrum of curvature perturbations zeta. Okay, so but I'm not going to do that in the notes. You can see that. Okay. So in particular, if I look at this, what you would find is it's something like phi bar dot var phi dot partial mu of y phi squared. Okay, that's what you will be finding if you do that expansion and keep cubic order in fluctuations. Okay. Then you could take this cubic interaction and you could, as an exercise, plug it into the in master formula, compute the bispectrum. Okay. In the notes I do this. Here I don't. Okay. I'm just going to give you the two main upshots of that calculation. The first upshot is that this bispectrum will peak for equilateral and will vanish for squeezed. Okay, and it basically vanishes for squeezed because one thing you notice here is that these fluctuations here always appear with a derivative acting on them. And that means if I go to very long wavelengths, it will get momentum suppressed because of these interactions that carry derivatives. Okay, and also it's not allowed to peak in squeezed, otherwise it would violate our single field slow roll, single field consistency condition. Okay, so it's just an example another example that holds. And in fact, in the squeeze limit, one finds that it vanishes. And even more than that, one finds that the rate at which it vanishes is governed by an analytic behavior of the ratio of momenta. So it's analytic in, say, K3 over K1 in the squeeze limit. Okay? And again, also this analyticity here is not a miracle. It's a consequence of this interaction being local. Okay? So there's a direct relationship between having local higher derivative interactions for the inflaton and analytic behavior in the squeeze limit. So this squeeze limit tells us more than just vanishing. Even the rate at which it vanishes has to be governed by an analytic function of the ratio of momenta. Okay? Okay, but this was for masses that are much higher than the Hubble scale. So what happens if that's not the case? So in particular, if the masses are less than or equal to a factor of a few times the Hubble scale. In that case, the field cannot be integrated out completely. So the field sigma cannot be integrated out. And so diagrammatically, if I spontaneously produce the field, it then decays pairwise into inflaton fluctuations. But I get some non-trivial, non-local correlations between these decay products because they came from from a common source. Okay, so the inflationary spacetime will spontaneously pair produce sigma particles because they're massive. They will decay. But that decay will be correlated because they have a common origin. Okay, so it's a causally generated non-locality of this particular type because these particles aren't massive enough to reduce this type of interaction to a point interaction. Okay, and one has to take into account this exchange of the heavy field. So as before, we can evaluate one of the legs on the background and the remaining three legs on the fluctuations. And so we would then get a bispectrum for the fluctuations. Okay? And you can calculate the momentum dependence of this particular bispectrum and identify the signature of the fact that there's this massive particle exchange happening in between. So we had non-local interaction which leads to a specific form for the bispectrum. And okay, again, I won't go through the exact calculation, but just it suffices to point out that this bispectrum now will be non-analytic in the squeezed limit. And this non-analyticity is a signature of the non-locality of this interaction. Okay. So in fact, let me actually write out for you what this squeezed limit looks like. So if I take the limit of K3 going to 0 of the bispectrum B zeta K1, K2, K3, there are two different cases depending on whether the particle is part of the principal series or the complementary series. We've seen that the superhorizon behavior of the long wavelength mode is different for the two cases, and so we expect there to be a difference in the soft limit behavior of this three-point function for this reason. Okay. And so indeed what you find is that first of all there's this overall exponential factor because of the Boltzmann suppression of massive particle production in the principal series. There's an extra factor of K3 over K1 to the power 3/2. This factor here is inherited from the tau to the 3/2 suppression of the long mode, which is given by K3 in this limit. There's a cosine of m over h times the log of K3 over K1. So you notice, all the time dependence that we saw earlier gets just translated into dependence on momentum ratios. Okay. So this is what you would find. So you inherit the oscillations that we had in the time-dependent mode functions in the momentum dependence of this squeezed limit. In the complementary series, you don't have these two suppression factors, and instead you get some non-analytic scaling of K3 over K1 to a power delta, where this delta is a scaling dimension which depends in a predictable way on mass and spin of the particle. Okay. So I actually don't have the formula with me, but it ranges from 0 to 3/2 roughly. So it interpolates this to this scaling, and K to the 0 in fact would be the massless limit. And so for massless particles, one would get no momentum suppression. For a higher mass particle, one gets a higher suppression due to this small momentum ratio here. Okay. But the nice thing is that it's still very distinctive. So you have this distinctive oscillations in one case, and you have distinctive non-analytic scaling in K in the other case. So if you could measure either of them, you would extract immediately information about the mass and the spins of the particles. In fact, given that I'm talking about the spins of the particles, so particles with spin have an extra dependence. So there is dependence on a Legendre polynomial of order the spin of the particle, with argument given by the angle between the vectors K3 and K1. Yeah, so what I'm looking at here is a squeezed limit where I make the triangle very squeezed, but there's of course still a dependence on how I'm approaching this squeezed limit can depend on angle. So I can go to the squeezed limit and I can then rotate the short momentum vector around. And so what I expect for a particle exchange for a particle with spin is that when I do this rotation of the long wavelength mode around some axis, that this would vary like a Legendre polynomial of order the spin of the particle. Okay? And the same up here. Okay? And so this is nice because it also allows us to extract information about not just the mass, but also the spin of the particle. Okay? Okay, and this is very similar to like what we do in particle colliders, and so that's why, in fact, this became known. These kind of features became known as cosmological collider physics. So this term goes back to Akani, Hamed, and Maldacena. And because what do we do in particle physics? In particle physics, if we want to identify the mass of a particle resonance, we measure a resonance, and we see some peak in some distribution. Okay? Here, these oscillations here in Fourier space, when you transform them, Fourier transform them become like a sharply localized frequency that depends on the mass. Okay? So that's like the resonance that we're seeing in colliders when we identify the mass of a particle. And in particle physics, the way we measure spins of particles is by measuring the angular dependence of the final state distribution. And so this is quite similar, that like if you think of the external states as being the zeta particles, then the angle between them in Fourier space carries information about the spin of any resonance that was occurring at earlier times. Okay? So that's why this is very, very much the cosmological analog of what we do in particle physics. So by measuring these type of features, we can determine the mass and the spin of very heavy fields. Okay, and the reason I call this very heavy is because you might have thought, oh, it's restrictive to be focusing on particles that are less than a few times the Hubble scale. But you should remember that the Hubble scale may well be as high as 10 to the 14 GeV. So by particle physics standards, it's not very restrictive at all. You know, like basically you would have access. You would be exciting every the spectrum of particles that exist, and up to that incredibly high scale. Okay. So if you think about particle physics units and then you compare them to the units that we care about during inflation, it in principle allows you to excite these very massive degrees of freedom. And finally, one of the reasons we would like to probe these very high, very massive fields is that we hope that they teach us something about the UV origin of inflation. Okay, so the UV completion of inflation, we think, involves extra scales and higher. Yeah, and then if you could excite particles at those extra scales, that would give us information about the physics of inflation. So, for example, in the most dramatic dream scenario, if you consider an inflationary scenario where the string scale isn't so far from the inflationary Hubble scale, okay, you might be even hoping to excite, a tower of higher string states, and those in the effective field theory would be represented by particles with discrete masses and spins, and a tower of higher spins. So, if you were able to measure correlated masses and spins of particles that trace out the Regge trajectory of a string, of course, that would be incredible. Okay, but that's a very far dream. So maybe on that positive note, I'll end this course. Okay, thank you very much. Yeah.
So here in this calculation, what's the role of the inflaton?
The inflaton here is the final decay product. Okay, so these things, because they're masses and they're at the minimal level, they're gravitationally coupled to the inflaton, they will not survive until late times. In fact, they will decay with time, and so they will then decay into lighter fields that are available, into which they couple, maybe gravitationally, maybe stronger, and the inflaton is the one candidate that's there. Okay. So we observe fluctuations in the inflaton or fluctuations in curvature perturbations. We actually don't directly observe. These guys will have zero amplitude at late times. So we never measure correlations of these massive fields. They're gone. Okay? But before they're gone, they might decay. And we see the decay products of these guys. And the decay products will carry signature of the nature of the thing that decayed. Okay? Well, yeah, we're measuring inflaton fluctuations in our detectors. Well, indirectly. Yeah.
When you said in principle for very heavy fields, so for example, I'm not sure if it's like when we get supersymmetric partners like coupled with photon, can we see them?
Yeah, so actually mentioning supersymmetry is interesting because imagine you take a bunch of fields that in flat space would have very light masses relative to the inflationary scale. If they're unprotected, then you would actually think that those masses will get quadratic divergences, related to the heavier fields that they couple to, and so they might be lifted to have very high masses. But in the case of supersymmetry, that lifting of their masses is restricted by the vacuum energy. Okay, and so during inflation, in fact, you typically generate then masses of order the Hubble scale, but not much higher than that. And the intuitive reason for that is actually if you think about bosons on fermion loops in flat space canceling because of supersymmetry, then the Hubble scale actually defines kind of the curvature couplings that change the propagators of fermions and bosons. So at very high frequencies, you approach flat space, so you should inherit this cancellation because you have high enough frequencies that you don't feel the effects of the curvature of the space. But at frequencies of order the Hubble scale, that cancellation will be spoiled and will not be perfect, and therefore you generate masses of order the Hubble scale. Okay. So that also makes it special. Why it also gives a motivation for looking for things that are not much heavier than Hubble, because if they were light in flat space, they get raised to Hubble, but not much higher if supersymmetry is there. And the nice thing about this is it doesn't really have that much to do about low scale versus high scale SUSY and so on. SUSY just has to be broken at a scale that's lower than the inflationary scale, which might not be very restricted. Yeah. No, that's lowering the energy, lowering. But not by very much, unfortunately. I think it scales as the fourth root of R. Yeah. So if you imagine in the future we will increase bounds on R by a factor of 10 to max 100, that doesn't actually change the energy scale of inflation by all that much. So, or turned around, if we want to have any hope of seeing tensors, inflation has to be near the God scale, give or take an order of magnitude. So it's not, we don't really have access to, if inflationary scale was that low, we don't have access to tensors. And in fact, yeah. So you would have to look for different effects to learn about the value of H when it's less than that. Tensors would only tell you about the value of H when it's close to the God scale.
Why is there this opinion that the only models that deserve to be called inflation are the ones that are measurable?
Is that there is opinion? Really?
But it's not.
I don't think so. I mean,
No. I mean, you can easily have. You just like to lower the scale.
yes.
Is there anything wrong with these models?
Of course.
They're more fine-tuned than you.
Yeah. Okay. I don't know. They're different. People have different opinions and so on. It's not very quantifiable, but yeah. One other way that we mentioned briefly last time was kind of the range of the inflaton evolution, and so that also qualitatively distinguishes things that produce measurable R and things that don't produce measurable R. And then if you look at the classes of models that fall into the two categories, the models that do produce R are simple polynomials like m squared, phi squared, and so on. And so what some people like about those is that they have just like, so it's like a very predictive, it just has one parameter. As soon as you go to levels of R that are smaller than about 1%, you can't do that with simple polynomials typically. And so you need,
for example, our favorite inflection.
Yeah, that has of course several, our favorite, no, our favorite inflection, well, the problem is that you also have to produce a global minimum. So what's special about m squared phi squared is that the same potential that describes the inflationary phase also describes the global minimum. So m squared phi squared has everything built into it. That's why it would have been nice. Yeah. So because while here this inflection point has a number of parameters. It has a slope and then it has a
Yeah, but with a polynomial, like with a few parameters.
Yeah. You can do it. Of course, you can everything. You can Taylor expand and so on. But the problem is this kind of feature if you write it out into polynomial language, means that you have to have some low polynomials and then some higher polynomials that balance each other to produce this global minimum. And to some people, that doesn't look very nice. Okay. Yeah, that's what some people, not even just for inflections, but for these plateau type things. That's one of the arguments that the people are using for the fine-tuning of the next generation of inflationary models that don't produce measurable R, is that they have to have at least 2 or more parameters to generate this type of behavior that it's inflating here, then it turns over and ends inflation, and then it turns around again to create a global minimum. Okay. I think the more promising way is actually not to think of this fine-tuned, for me at least. If you think of this as an artifact of trying to describe things in terms of one field. So for example, there are things like hybrid inflation models that have 2 fields. One field that governs this type of regime, and then a second field that governs the exit. Okay. So you can, and so it looks the second field has some kind of waterfall-like instability, or like the Higgs potential type instability. And so that you're rolling this way where the field is stabilized in the second direction for a while, and then it turns over and gets destabilized. That's generated by a very simple coupling, yeah, phi squared, chi squared. Yeah. But from the point of view of, if you try to represent that by a single field, it might look something like this, have a sharp edge. Okay, but really what that sharp edge just corresponds to is a instability that's triggered by moving through some critical field point. So that's how I think these things don't necessarily have to be unnatural when expressed into this high-dimensional field space.
How sharp the edge should be?
Which edge? This edge? I think it depends a little bit on the model shape. So there's some integrated constraints that you want to evaluate your fluctuation 60 e-folds before the end, and so that will give an integral constraint on the integral of 1 over square root of epsilon of phi over phi and so on, and so that will kind of be. So the point being that if you make this transition too slow, then you will spend actually most of your inflation in the transition. And then you're not in the regime where you think of this as like a flat plateau and then ending, but actually it's just a hilltop where you're rolling off. And that might be fine too, but it's not this picture, yeah? And so therefore, there's a continuous interpolation between just rolling off a top, yeah, and having a flat plateau and then sharply ending it, okay? And you want to end it sharply because then it means that the 60 e-fold mark, when you evaluate your fluctuations, was in the plateau region and not in the transition. Okay. Yeah. These that depends on the amplitude, okay? And so yeah, because in particular it depends. In this toy model, okay, it depends basically on how strong the coupling is. One of the factors that enters, and it's hidden here in the proportionality that I've written. It's how big the scale lambda is, yeah. And so what Akani Hamed and Maldacena, I think, were assuming for most of the paper was the maximally conservative thing, where this coupling here is gravitational. That's the Planck scale, and that was nice for them because that also means that all the interactions at an approximate level satisfy conformal symmetry, and all the structure of what I've written down here, they derived without even using a Lagrangian and just by symmetry reasons. Okay, it's very beautiful, very pretty. Okay, but it doesn't necessarily have to be that way. This scale lambda can be much lower than the Planck scale. I think the lowest you can make it is the Hubble scale or something like that. And so, but there is 5 orders of magnitude between the Planck scale and the Hubble scale, and then this depends actually on the square. Or the answer will depend on the square of that ratio. So there's a lot of room depending on how strong we make that coupling. And of course, that room means the signal can be large, but unfortunately it also means that we can't make, it's a continuous parameter that gets pushed down as we're not seeing anything. Okay. No, well, maybe I go back to this plot. So maybe let me rephrase your question so that it's easier to answer. Okay, and then the harder question I can answer afterwards. Maybe. Okay, I'll try. But so notice that I was mentioning this regime here as being the regime that we, the signals could still live in. So you might now ask, okay, with future CMB measurements, how far into this regime can we dig? Okay, and so roughly speaking, I think for the CMB, we will not be able to dig into this regime by more than 1 or at best 2 orders of magnitude. Yeah, so you will be able to constrain it further here up to 10. Yeah, then future large-scale structure measurements might give you an one extra order of magnitude. Maybe if all really goes exceptionally well, maybe you get to values of 1. Okay, and then this remaining 2 orders of magnitude, there's some dreams of having measurements of 21 centimeter fluctuations from the backside of the moon and those kind of things. That will be, in principle, just by counting the number of modes that you have available in those kind of signals, would allow you to close this window. And then even seeing, and then at some point you have to see something. That's also, so you have to see this gravitational interaction. But that's far way off. But it's far away off, but you guys are young enough. So, and if I keep healthy, maybe also. But
okay, so we can ask more questions
yeah.
during the discussion. Let's thank Daniel.
Okay.